So to go back and start at the beginning, for pulsars anyway, and for me, because it's the year I was born, 1967, pulsars were discovered by a graduate student, Jocelyn Bell, and working with her advisor, Tony Hewish, in Cambridge. They built an 81 megahertz radio array in Cambridge. She put it together with her hands with baling wire and wrenches and chart recorders and solder and all that, and they were looking for interplanetary scintillation. And she was sharp-eyed enough to notice on her chart recordings that sometimes what they were not seeing was interplanetary scintillation, but was a periodic signal. And the first pulsar that she discovered, once she tracked this down, what are these periodic signals, she looked back at them the following day, and they occurred 4 minutes later, which she knew was the difference between the solar day and the sidereal day, so this must be something from this cosmos and not from the Earth. And she discovered this pulsation at 1.337 seconds, and it was quickly found other examples of that, and those were named pulsars because of their pulsing radio emission, and very quickly thereafter they realized what they were, which I'll show you in a second, and published a paper on it, for which her advisor won the Nobel Prize. Jocelyn, of course, is still super active and is head of the Royal Astronomical Society, and is an incredible scientist. So pulsars, we now know and understand them over the last 52 years, that they're neutron stars, which are born in the collapse of a massive star. When you have a star that's more than about 10 times the mass of the sun, instead of collapsing like our sun will to form a white dwarf, it has so much gravity. The white dwarfs, you may know, are these small hot stars about the size of the Earth that are supported. When you try to press matter together, it's no longer generating heat to puff up. The matter presses together. It's supported by the pressure of electrons against electrons, called electron degeneracy pressure. When stars are even more massive, that electron degeneracy pressure is not enough to support it. They collapse down. The electrons and protons are pushed together and form neutrons. Now there's no charge pulling things apart. They collapse down to be even smaller. And those are called neutron stars because they're predominantly composed of neutrons. These are the most dense objects in our galaxy, in the universe. They're any more massive and they would collapse completely out of the universe and become a black hole. So if you take something the size of our sun, which is spinning about once a month, as you may know, and collapse it that far down, of course it's going to spin faster. And so these things are born spinning incredibly fast, and pack 1.5 times the mass of the sun into something about the size of the Washington Beltway, although this one is a picture of a neutron star above the San Francisco Bay Area. But that gives you a sense of scale of how big one of these stars is. 1.5 times the mass of the sun packed into the size of a city. So there it is in space spinning and emitting radiation along its magnetic poles. So there's a number of different pulsing neutron star type phenomena. The one I'm going to focus on for this talk are the so-called rotation powered pulsars, the ones probably most of you think of when you hear the word pulsar. But just to be specific, we're going to talk about the rotation powered ones. Those are the ones formed in supernovae. They start out spinning fast. That very fast spin, coupled with its very strong magnetic field, means that it is an incredibly energetic system. That rotating magnetic field generates electromagnetic radiation. When you spin a magnetic field, it generates electric fields, which accelerates particles, so they are also prolific emitters of particles, which form some of the cosmic rays that impact our Earth. And because they're just born with spinning, they don't have any other source of new energy, they slow down as they age. They spin, they lose energy, and they slow down and slow down and slow down. All right, so most pulsars we studied the discovery of was in the radio wavelength. And people often say that radio telescopes are like listening to something. Of course, it's not really like listening because your ear doesn't sense electromagnetic waves, but you can take those electromagnetic waves from a radio telescope, detect them, and feed them into a speaker and hear the sound of a pulsar. This is a slow pulsar pulsing at about once a second. You can hear the pulse as the beam of energy crosses your line of sight. So yes, sort of like a lighthouse. It's basically the reason that they pulse. They're not turning on and off. The beam is just sweeping past our line of sight periodically. So That's a slow pulsar like the ones that were first discovered. So they're amazing astrophysical, objects for astronomy where they're the way that stars are formed and die, and the evolution of matter in our universe, and all these really interesting astronomical objects. But also, they're incredible probes of extreme physics. These are, as I said, they're the most dense objects in the universe. The cores of neutron stars are more than twice as dense as an atomic nucleus, and that's a condition that you can't make anywhere in a terrestrial laboratory. So the only way to study matter at that density is by looking at these neutron stars. They are incredible extremes of gravitation. They're the mass of the sun, so they don't have any more gravity than our sun, but they're incredibly small, so you can get very close to that strong gravity and have incredibly strong gravitational curvature. And also, they're very nice clocks, as you saw. And if you put a clock, especially if you have two, in orbit around another clock, you can do incredibly precise general relativistic experiments. And the first demonstration that gravitational waves existed was in observing two pulsars, and we saw them spiraling in towards each other in exactly the rate predicted by general relativity if they were losing energy through gravitational waves. And that discovery was by Joseph Taylor and Russell Hulse, and they, again, won a Nobel Prize for that work. And so another thing that's at the cutting edge of pulsar timing work is to use these precise clocks to try to directly detect gravitational waves from the early universe. We saw some interacting galaxies in one of the pictures earlier. Galaxies that are spiraling in towards each other like that are what forms larger and larger black holes at the center of galaxies. Those forming black holes are emitting gravitational waves, massively strong gravitational waves, but they're super far away. But there's many of them all over the universe, and so that cacophony of gravitational waves coming and hitting the Earth can in principle be detected by looking at the pulsations and pulsars and timing them very accurately, and we're working on that now. Detection has not happened yet, but we expect it within the next few years. They're extremes of magnetism. Their magnetic fields are the driving force behind all the phenomena that we see. And some pulsars have magnetic fields above the so-called quantum critical limit. Incredibly strong magnetic fields. Again, that is something you can't create in a lab. And they make extreme particle accelerators, I mentioned. They accelerate material as they hit their companion stars or just in the magnetospheres, and make electron-positron pairs and gamma rays that we see with gamma ray telescopes. So they're really amazing physical probes. All right. So I wanted to give you one famous pulsar example, the Crab Nebula with its central pulsar. So remnant here, super remnant M1, for those of you that follow the Messier catalog. It's got a very fast pulsar in it, born on July 4th, 1054, one of the few pulsars that we know its exact birthday from historical records. And it spins at about 30 times per second. So I have a sound of that. It's a 30 hertz pulsar. Not very pleasant. So it's one of the few pulsars that we actually see in the optical band. As I said, most of the energy that comes out is sort of what we call non-thermal emissions from accelerating particles and things like that. So it generates rapidly moving particles, which makes radio waves, might make X-rays and gamma rays, but most of them are not seen in the optical band. This is one of the few that is, and there's even stories of some people being able to see it with their eye. 30 hertz is right at the limit of where the human eye can discern something, and there's been claims of people looking through on star nights at large telescopes, being able to detect the blinking light from the pulsar at the center of the Crab Nebula. All right, so they're born spinning about as fast as the Crab, tens of hertz, and they spin down and go slower and slower and slower as they go. Let's take a second to explain this. This shows a plot of all the pulsars that we know with their period, how fast they're spinning, 1 second here, 0.1 seconds, 10 seconds here, and then their spin down rate, how fast they're slowing down. Don't worry too much about the units. But you can see basically that when a pulsar is born, the very young pulsar that we know here, the Crab, is born spinning fast. As it slows down, it spins slower and slower and slower. At some point, it slows down enough that it's not that the spinning magnetic field is not able to generate a strong enough electric field to create those electron-positron pairs that power its emission, and it sputters out and becomes a dead pulsar, just sitting there doing nothing. That's what happens to most pulsars. So there's a few very young ones, a lot of middle-aged ones, and then they cross the death line here, and they enter the pulsar graveyard where we don't see pulses anymore. And that would be the end of the story for most pulsars. But the lucky few of them have a binary companion. And when that binary companion evolves, it grows larger into a red giant or similar star and dumps material onto the pulsar. Now the pulsar is accreting material that's falling onto it that can spin it up, making it go faster and faster and faster until it crosses back into the region where it has enough energy, enough spin to be able to create pulsars once again. And these are now, with their magnetic fields greatly reduced, so the spin down rate is much, much lower. They spin down very, very slowly, but they're spinning much, much faster, hundreds of hertz. So those are called millisecond pulsars. And this video shows you how they are formed. Here is a pulsar that's dead and you can't see it at all. When its companion evolves, matter starts to fall into an accretion disk, and it starts accreting matter onto the star. And now it's going to zoom in, and you can see that the pulsar is still spinning slowly, but the accretion disk is spinning fast. As long as the accretion disk is spinning faster than the pulsar, when it attaches onto the magnetic field here, it will add an angular momentum to it. More and more and more. Now you'll see the pulsar start to spin faster and faster and faster until it's spinning at the same rate as the Keplerian velocity, the orbital velocity at the edge of the disk. And then it reaches equilibrium, and eventually that star, the companion star that's dumping that matter, goes through its life cycle like our sun will, becomes a white dwarf. It's no longer dumping matter onto it, and you end up with a millisecond pulsar and a white dwarf in a binary system. And that's the way we find most of these millisecond pulsars in that situation. So millisecond pulsars are spinning at hundreds of times per second. That's incredible for something that weighs 1.5 times the mass of the sun. So it's hard to sometimes get a feel for how fast that is, but I looked it up. A Vitamix blender spins at 380 hertz, 380 cycles per second. This pulsar that I'm going to tell you is to play for you is 1937 plus 21, the first millisecond pulsar that was discovered. It's 640 hertz. Now this is faint pulsar. It's difficult to hear, so I'm going to play it two different ways. This is a recording from the Arecibo telescope, the largest radio telescope in the world. It's in Puerto Rico. It's 305 meters across. So an enormous telescope. But even with that, it's very hard to hear the individual pulsar. So you'll hear the tone. It's buried in noise, so you don't hear it very well in the first one. And the second sound is processing that with a filter that isolates the sound of the pulsar so you can hear it more clearly above the noise. There it is without processing. Yeah, so that's what a millisecond pulsar sounds like. Still wouldn't want to make a song out of it. But because they have been, their magnetic field has been reduced and they're spinning down very slowly, there's not very much torque or any disturbance acting on them at all. They're like a giant ball in space that's just spinning with almost no forces on it. So they're incredibly stable clocks. In fact, this pulsar will slow down, spinning its period of 1.56 milliseconds. Its period will change by 1 microsecond in a million years. That is an incredibly good clock, much better than your watch. So, in fact, it's better than a lot of it's better than a lot of laboratory atomic clocks on long time scales. I'll show you that in a second. So, as I mentioned, these millisecond pulsars and pulsars in general are multi-wavelength objects, mostly not in the optical, not in the bands that you typically observe in, but they're very powerful gamma ray emitters. We study them with the Fermi Gamma Ray Space Telescope, which was developed at NRL, one of the instruments. That's where a lot of their energy comes out from those accelerated particles, and that's where this is the kind of gamma ray telescope that reveals new pulsars on the sky. And we learn about the formation of them and a whole host of things from gamma rays. I'm not going to talk about gamma rays today. And I guess I'll say it again, the radio pulsars is where they were discovered. The first pulsars were discovered in radio, where most of them are still discovered and studied. There's well over 2,000 pulsars now, and over 200 of those are these millisecond pulsars. And that's where we get our most precise timing. And NanoGrav here is that project that I mentioned that's trying to detect gravitational waves from the early universe using pulsar timing. Today, I'm going to talk more about what we get from the X-ray band because of our new instrument, NICER, which is on the International Space Station. In the X-ray band, we get a view of them that's a little bit different than we see in other bands. One is that in the radio band, I guess I didn't really talk about that yet, but in the radio band, the signal is corrupted by traveling through the interstellar medium. The interstellar medium is not quite a vacuum. It's a very tenuous plasma, and that causes distortions in very much the way that seeing in the optical as light travels through the turbulent atmosphere, you get that kind of effect in the radio. So that provides a limit to how well you can do. In the X-rays, those effects are not there. They're at effectively infinite frequency, and so you're free of any propagation effects on the timing measurements that you make. We also get to see, very importantly, the surface of a neutron star. You can see hot emission from the surface of the neutron star. In the gamma rays and the radio waves, we're seeing emission that comes from out in where the swirling magnetosphere is, not from the surface. But in the X-rays, we can directly see the surface, and that's really important because that can allow us to make measurements that constrain the size of the neutron star. That's something that no one has been able to measure precisely so far. But if you could learn about the physics that goes on at the very core that we don't understand, that current nuclear physics can't explain, and we don't know what's going on at the core because we've not been able to study, and we can't do the calculations to know what goes on at those twice nuclear density. So that's a very important science goal of NICER, is to try to make the first very precise measurement of a neutron star radius. And we also see other emission from the magnetosphere. So I mentioned what these pulsars are, and that about 75% of them are still in the binary systems that were what formed them when they spun up, right, and created from their companion. What we see now is that when we look at them in the X-ray band, is that there's basically two classes of them. One of which that have so-called non-thermal emission. It's not the thermal emission from the not hot surface, but emission from the outer of the magnetosphere. And those are the ones here in the right-hand column that have very sharp pulses, which is very good for timing. So these are the ones that we can see at higher X-ray energies and with very sharp timing features that we can use to make that are very, very good clocks. The other ones are the ones where you're seeing hot emission from the surface, and so their pulse profiles. These are just like the light curves that she showed at the AVSO stars. These are just the data from X-rays from these neutron stars folded at the pulse period, so that you can see what the pulse shape looks like, just like those variable stars that were eclipsing or whatever. So these ones have much smoother pulse profiles because you're seeing a hot spot on the surface going in and out of view as it rotates around. So there's basically two different classes of X-rays and millisecond pulsars. Yeah. So I mentioned that they are really good clocks. This is from a study that was done by real clock experts. Basically, it's very hard to make a measurement of a pulsar on a very short time scale. So on a very short time scale, if you're trying to measure the period of the pulsar, you don't get a very precise measurement. But because the period underlying is so precise, you can come back and years later and make another measurement of when the pulse arrived and know extremely precisely what the pulse period was. So the longer you integrate, the more precise your knowledge of that frequency is. And that's true for any kind of clock. And so this is a comparison of some atomic clocks, very precise laboratory frequency standards, which on short timescales are way better than pulsars because they're made by people who know they want to measure them, so they make the signal so it's very easy to measure. But so you can very precisely measure the frequency of your atomic time standard in the laboratory over a short time scale, seconds, minutes, hours. But it's extremely hard to control the environment of your laboratory time standard because there's changes in temperature, changes in humidity, thunderstorms passing by, jiggles from the Earth. And so there's always, as you try to extrapolate your time further and further into the future, your clock gets less and less precise. And the way that's dealt with on Earth with all the Naval Observatory and other laboratories that do time standards, they combine into an ensemble, many, many clocks from all over the Earth. And the time standards that are published, that's what you set your watch to, universal time, is really the average of many, many clocks. But on long time scales, millisecond pulsars become as good or better than even the very best atomic clocks. And we take advantage of that you can use them like we use GPS, which is as navigation sources. What it does is this is your phone here, and this are GPS satellites. So the GPS constellation has a large number of satellites orbiting the Earth, and they broadcast signals from each satellite that goes out and is received by your receiver in your car or in your phone. And the signal says, hey, I sent this signal at this time, and I was at this location. And now your clock receives it, and it says, I know this guy sent me a signal at a particular time from this location, and this person sent one from this time at this location. It took the light this long to get to me, so I know exactly how far away that satellite was and in what direction. And then I know how far away that satellite was and in what direction. And then you do that a few times, and you can locate exactly where you are. That's called trilateration. It's like triangulation, but with distances. That's how your phone solves for where you are and what time it is. We can do the exact same thing with pulsars, where we know from studying them for a long time very precisely when I expect each pulse to arrive at some fiducial point, and I can measure when it arrived at me, and then say, well, that tells me how far I am from the fiducial point that I expected it to arrive. And that gives me an error signal that I can feed into my system and tell where I am. This works only in space because the X-rays from these pulsars don't make it through our atmospheres. You have to study different space. But for a spacecraft to tell where it is, you can do it using pulsars just in the same way as you do on the ground with GPS. So now I'm going to tell you about NICER. NICER is an X-ray telescope. It's on the International Space Station. And it had dual goals: to be able to, one, study the astrophysics of these pulsars and understand them as astrophysical sources and do the physics to study their interiors and all that. And two, to do the first demonstration of this pulsar-based navigation. And we have done both of those things. So NICER, the PI is Keith Gendreau at NASA's Goddard Space Flight Center over on the other side of the Beltway. It's a soft X-ray telescope with incredibly good timing and spectroscopy. It was launched about 2 years ago in 2017 on a SpaceX rocket. It's now attached to the International Space Station, as I'll show you. And we've just completed 2 years, our 2-year baseline science mission. And thankfully, NASA headquarters has just given us a 3-year extension. So we'll continue to do science from the space station for the next 3 years at least. It is in the 0.2 to 12 keV, kilo-electron volt band. That might not mean too much to you, but it's the soft X-ray band, a little bit below the X-ray energies that are used for your dentist to take an X-ray of your teeth. The optics are interesting for those of you who are telescope builders. They're concentrating optics. They're not good imaging optics. They just concentrate onto a single pixel. So it's like a photometer, not like an imager. And that is a decision to make it very inexpensive to create a large amount of collecting area. You can imagine it's a trade-off between imaging quality and collecting area. And we chose to get as much collecting area as we could for as cheap as we could and give up imaging. But we have very good timing and spectroscopy. And the enhancement, as I mentioned, was the pulsar-based navigation. We're trying to understand the nature of the ultra-dense matter at the core of neutron stars. We're probing all the dynamic processes that happen in these really rapidly spinning and amazing objects. And we can do spectroscopy of all sorts of time domain flaring objects. We do black holes and different manifestations of neutron stars. We see thermonuclear bursts on neutron stars. We see just tons of different types of science. But a lot of it has been focused on understanding neutron stars and their properties as very precise clocks and understanding what's going on at their cores. So let me just show you what it is. This is it. This part is attached to the space station. This is the business end. It's got 56 co-aligned X-ray telescopes. Each one has got a front about the size of a CD-ROM. And they focus down at the 1.25 meter focal length onto 56 detectors in the back here. These are sun shields that you can see. There's a star tracker camera that tells us where we're pointed, electronics box, and pointing actuator. And a little video of it. When it deploys, it goes up like that, and then it tracks the stars by moving around on its little wrist there. Because you may not know, the space station flies over the Earth not in an inertial way, but with its one end pointed at the Earth all the time. So the sky is moving all the time with respect to the space station. So if you want to observe a fixed star, you have to keep turning, just the way you guys do with your amateur telescopes on the ground. You have to have a motor so that it stays on the star you're doing. Exactly what we're doing here. All right, so this is a little personal account of the SpaceX. If you have never seen one, I highly recommend seeing a SpaceX Falcon 9 launch. They're incredible. This was June of 2017. This was the 100th launch from Launch Complex 39A at Kennedy. And it was the first one using a reused Dragon capsule. SpaceX is doing amazing things with reusing boosters and capsules and even fairings now. So it's really incredible. This is some of the pictures from the launch, a long exposure from it. And then just the most amazing thing is that the booster comes back down and lands right there on the ground about 3 miles from where it took off. That is a real sight to see where it is, right? Missed by what? 20 feet? And then it comes back out again. It's like a flaming pencil falling out of the sky. And they warn you that when it lands, right after it lands, you hear a really loud explosion. And that's just actually the sonic boom from when it went across the sound barrier, which takes a little while to get to you. So it kind of happens at the same time it lands. Don't worry, it actually will. So then we go up into space. We're in the so-called trunk of the Dragon. This is us in the backside of the Dragon capsule, carried up to space station. Here we are up attached to the space station. You can see clouds reflected in our heat shield. So this is a radiator that radiates from the electronics, so it's very shiny. And you can see the clouds reflected in that. So we wait to be carried away. And then this guy, the Dexter manipulator arm, comes and grabs us out of the trunk and carries us over to quite a long time, a day or so, to get us from there over to our final docking spot. So if you see a picture of the space station and sticking up is us right there, and you'll see us moving around the space station flying. These are huge solar panels that power the space station. These are radiators that radiate away all the waste heat. Those are. There's a docked vehicle. So it's just an amazing, busy place, and we're using it to do X-ray astronomy. And it's an interesting place to do astronomy. Most of the time it's done from free-flying satellites. Here we pay a price, and that there's a lot of extra safety requirements because of humans on it, and you've got these giant things waving in your view some of the time. But the benefit is that someone else paid the $100 billion to build this. And it's got incredible data rates. We just plug into the internet. You can carry almost as much weight as you want, with tons of power. So you get some real benefits for it, for doing science on it. And this is what it really looks like. You also have the benefit of having high-definition cameras looking at your experiment, which is not the case for Chandra and Hubble and all these other satellites in space. You normally don't ever get to see them once you launch them. We can watch ourselves in HD TV while we do our operations. This is sped up, obviously, a lot. But that's what we look like doing our business on the International Space Station. So it's really kind of mesmerizing. So you'll see it go and acquire a new source, track it over. And of course, we have big 3D models of all this junk so that we don't point at the solar panels and miss the star that we're seeing. So we schedule around all the activity that's going on the space station. It's, like I said, not imaging. but it has a small field of view, about 6 arc-minutes in diameter. And so we only get the X-rays that come from that 6 arc-minute diameter and block out everything else that we collect. And for the Crab, it's a very bright X-ray source. The Crab pulsars that we showed you earlier, that generates about 38,000 X-ray counts per second in our detector. So that sort of sets the scale for us. It's very, very capable detector. It has really good energy resolution, has a very low background. So less than 1 count per second of background, and 38,000 counts per second from a bright source like the Crab. Really good. So this is just an example, a comparison. This is the X-ray energy, and this is the collecting area of the telescope. XMMNewton is the previous best telescope for doing this kind of pulsar timing. It's almost $1 billion class European mission. And you can see that we have twice the collecting area of the previous $1 billion class mission, and we're a $60 million class mission. Remember how did we get that? Give up imaging. That's the difference. So I showed some of those earlier plots of X-ray pulsars. Here's the kind of plots that come out of NICER. So on the top are some of the earlier XMMNewton results, and on the bottom are some of the NICER results that we're getting. And you can see for a lot of these pulsars, we just get vastly more signal to noise, vastly more significance that allows us to study what's going on the surface of these stars much more precisely. And for this pulsar, there is no XMMNewton panel because they were not able to, they never observed it in a mode that could see it. They were not able to see it like this. So NICER discovered the X-ray pulsations from that pulsar. So those are the raw data that we kind of do all of our work with. So now let me just turn to Sextant, which is our name for the demonstration of pulsar-based navigation, Station Explorer for X-ray timing and navigation technology. So this was funded separately from NICER. Most of NICER was funded by NASA's Science Mission Directorate, but we were funded by the Space Technology Mission Directorate to do this pulsar navigation. And the goal was to implement fully functional pulsar-based navigation on board, on orbit. Not taking it to the ground, crossing to show that you can do it, which we had done before, but doing it for real in orbit with a goal of 10 kilometers, a requirement of getting to 10 kilometers accuracy over this whole time that you're doing it, and a goal of reaching down to 1 kilometer accuracy. And so we did that by taking over NICER from the scientists, so to speak, for periods of a few days to a couple of weeks, where we got to schedule, we got to look at whatever pulsars we wanted to that were in the order that you want for navigation, rather than in the order or the priority that you want for science. So we took over it, used it for a couple of weeks, let the onboard software run, and validated that it worked. And then, of course, we do lots of ground experiments using the data that we collected to try different scenarios and things like that, and do other things like that. So, just very briefly, the history of using pulsars for navigation goes way back. Very shortly after pulsars were discovered, it was realized that you could use them as something to point out where you are. And in fact, the Pioneer plaque, these pointers here, are encoded in some kind of code along each one is the pulse period of a number of pulsars and the directions to them from sun, so that if alien civilization finds it, they would be able to locate the solar system with respect to a number of pulsars. So that was done even back in the 60s and 70s. We did the first experiment at NRL that was dedicated to trying to do precise pulsar-based navigation called USA, that we flew, and we worked with some graduate student and a professor at the University of Maryland to develop the navigation algorithms, and that led to our patent. This was all done, as I said, with ground-based processing. We took the data and processed it on the ground. Then DARPA funded a program called XNav. They built a jazzy logo, where 2 different teams developed, pushed the development of detectors and navigation algorithms, system architectures, and things like that. That helped a lot to get us further down the road, but they didn't proceed because they didn't want to spend the money to build an actual flight experiment. But that then led to NICER and Sextant that was selected finally in 2013, and as I said, launched in 2017. So this is how it works. Basically what I said before, the pulses from a pulsar come, they hit you at the spacecraft, and say that you know where the pulse, what time the pulse would have arrived at some position, say So the center of mass of the solar system is the typical reference point we might use, or the center of the Earth, either one. And if you know when it hit you, and you know when it was supposed to hit here, you get a measure of the time it would have taken to fly from here to here in the direction of the pulsar. If you do that in several different directions, you can tell where you are. And for reference, for the speed of light, 1 microsecond. The speed of light is 300 meters. So if you could measure the arrival time of your pulse to 1 microsecond, you can measure your position to 300 meters. If you repeat in different directions, you get to solve for your full position in space, and if you have at least 4, you can solve for your clock as well. I conveniently numbered the pulses here so that you know which one they were. In actual fact, you don't know which pulse you're seeing. So you have what's called an integer phase ambiguity problem, where you don't know which integer you're on. But if you knew the right answer, if you were close enough to it that you knew which pulse it was, you could figure it out. So sometimes you have to do it iteratively, but once you're kind of locked on, you can stay locked on. So it is a challenge to determine that initial solution, which you can do by bootstrapping from slower pulsars to faster ones. But yeah, unfortunately, unlike GPS, they don't come with a label. The photons come in, are detected, go to a pulse integrator, which makes those light curves, just like the AAVSO ones, or like the ones I've showed you, make those light curves. We have the timing model that tells you when that was supposed to occur, and then we compare them, and we get a difference between when it was supposed to occur and when it did occur. But to do that, I have to know where I am in order to fold those pulses correctly. So that's the job of an orbit propagator, which takes where you are now and the knowledge of how you're orbiting the Earth and propagates forward to figure out where you would be at any given time. And so it's important that orbit propagator is correct and good enough to get you through the time that you're trying to integrate from one pulsar and then go to another pulsar and another pulsar so you can stitch them together even though they're taken sequentially. If you didn't know anything about where you were and you just made one measurement and then you made another one and you had no way to connect them, you wouldn't be able to do it. But because we're moving in a gravitational field that we know quite well and we know the velocity of the space station pretty well, once you have your solution, you can continue and take data sequentially and put those together, and it works fine. NICER had one big cheat, is that we used the photons that came in are timed to GPS because we have a GPS receiver on board. So the times were perfect. We didn't use a GPS receiver at all to process the photons for positions or anything like that. So the demonstration was completely true, except that we had perfect time. So in a real situation, you would have a free-running atomic clock on board, and it would not be perfect. And you'd have to solve for the clock offsets as well. And we couldn't simulate that on orbit with NICER because we had GPS and the times were just correct. So what we did is we took the data on the ground. That was one of the ground experiments we did. We fuzzed the clock on the ground by intentionally introducing a drift into it, and then ran our algorithm and allowed it to solve for the clock offsets as well as the position, and it was able to do both. So this was the demonstration we did. This is the observing schedule. So these are 1, 2, 3, 4, 5 pulsars, and this is the day of the year. And this is the times that we were able to observe that pulsar. So each pulsar we go and look at 0218 for a little while, we go down and observe 1821 for a little while, and 0030. So we're cycling from one pulsar to another. We stitch those together into measurements, and this one takes a tiny bit of explanation. This is the error in our current position estimate, and this is the time, day of year. If you don't have the pulsar measurements, your propagator starts to wander off because it's not being guided by anything, and it does this blue line here. So you start off knowing where you are pretty well, and then all of a sudden you don't know where you are very well. It diverges rapidly, and you don't have any idea where you are. When you add in the pulsar measurements, you get the green curve. It starts to diverge in the same way, but then boom, you start to get measurements from the pulsars. The Kalman filter starts eating those up and improving its knowledge of the orbital trajectory, and boom, 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 you get down there, and then it reaches a steady state where you know you're keeping track of the orbit of the space station to better than 10 kilometers for indefinitely. So that's pretty cool. But my watch can tell where I am better than 10 kilometers. Why do I need this one? So what do you want it for? So there's a number of different reasons. One is that for deep space mission, NASA's very interested in it. They're looking at some very deep space missions that go out well beyond the outer planets. Outer planet missions currently rely on a thing called the Deep Space Network, very large radio telescopes that talk to the satellite. Every time you talk to a satellite far away, you send it a signal and it sends an answer back. That's a round-trip time measurement, so you can tell very accurately how far away that is in that direction. It's much, much harder to tell where it is in the directions on the sky, the cross directions from that. That requires another technique where they take multiple radio telescopes and put them together and make an interferometric measurement. It's really hard, it's expensive, it uses a whole lot of resources, and the farther away the satellite is, the poorer that gets. That's not the case with this system. It works wherever you are without using any resources on the ground at all. All you do is once every year or whatever, update some new timing models for the pulsars, and it can tell where it is autonomously in all directions equally well. So great for deep space. Another reason might be for human missions, where we're starting to, again, send humans out to the moon and possibly to Mars. Human missions do not have a tolerance for failure, because we don't like to watch people die on TV. So they are worried if something happens. They say they lose their antenna, or there's an Apollo 13-like failure. You don't want to be reliant on one antenna that talks to the ground for your only navigation. So if you have a backup system, maybe it's not quite as good, but it's more resilient, where you could lose communication with the ground for whatever reason and still be able to complete your mission and navigate and not kill people, that's a good thing. And also the similar system for national security. We have a lot of satellites, you probably know, that are doing a lot of important things for national security. Many of them rely on GPS or other clock technology, and we are always worried that someone can deny the GPS or the GPS failure or whatever. So this can provide a resilient system to steer clocks for long periods of time without needing to rely on GPS. So those are some of the kinds of things that people are looking at for the future. And then on the science side, I have to advertise this. So NICER was these 56 X-ray telescopes, and it's been 10 times. It's much larger than previous missions, and it's doing incredibly good things on the space station. We have a vision for the future that the community is now considering as part of what's called the decadal survey process, or what the NASA should do over the next decade. It's called StrobeX. It's 10 times the collecting area of NICER. It also has a harder X-ray instrument on it as well, and an all-sky monitor. It's called StrobeX, and so it's a massive $1 billion class mission to take this to the next level. And we have developed that over a couple of years in a big concept study to show that it's achievable and doable for the budget proposed. And we have got stickers, and we're on Facebook and Twitter and everything like that. So that's hopefully the future, which would launch in about 2030. So I can come back and do a talk now. All right, thank you very much.